All right. We're so damn tired. Perk up. Don't give up. I know everyone's exhausted. I know. I'm not blaming you. But got 2 more weeks of this to go, right? Wasn't that weird? It's like 2 weeks of this class and then final. Is on Monday. No, not this Monday. No. So the calendar I want you to have in your head is this, right? This is the calendar. So next week on Friday is exam 2. That's March 4th. That's exam 2. Then we have 1 week of, then there's the week after that, the last week of classes, then comes the last week of classes. Then comes final. This period has the final on Monday. Man, it's like just crushing the end of the quarter here.
What do you know what time the final?
I do. It's from 1 to 4. It's better than 7 o'clock in the morning.
The next day I have 7 a.m. to 10 a.m. and then 7 p.m. to 10 p.m.
Oh. Okay, never mind. That sucks. That's terrible.
Yeah.
Yeah. So we're basically probably feels like this is all going really, really, really fast. Hopefully you guys have a nice break plan for the 1 week that you won't be in school before we got to come back in and crush it again in the spring. Okay. Are there any questions about any of this stuff? So next week on Monday, so next week on Monday, I'll kind of walk you through. It's the same deal with the exam. We have a couple more sections to get to prior to the exam. And then on Monday, I'll kind of walk you through what's going to be on it. And then I'll post probably on Tuesday, a review just like last time. So this will be, I think will be content complete for the test after we do 13.2, right? So at least some part of 13.2 will be on the test, and then there won't be any more. Any other questions? Structural calendar-wise? What day is 13.2? So I'm going to talk about 13.1 tomorrow after the quiz, and then I'm going to talk about 13.2 on Monday, and that'll be it. 13.2 may go into 13.1 and 13.2 are sort of the beginning of calculus or vector functions. 13.1 is about being able to draw them in 3 dimensions and what a vector function is. 13.2 is your beginning of differentiation and basically a differentiation in that context. And then 13.3, I'm considering leaving off to the final because 13.3 is really, it's the most useful calculus of vector functions because it covers arc length and curvature. And you guys, I don't know if you've seen normal, tangent, and binormal vector frames on moving curves before. So it's really cool idea, but it seems like a lot to try to crush that in, prior to the test. So, I don't have anything prescribed in mind. If I don't get it, whatever I get to basically by Monday, that will be when I'm still responsible for the final, but I will close off. It'll be very clear what the closing point is for the exam. Okay. Any other questions? All right. Sorry about the heat. There's no control over that. Anybody sitting here boiling like me. Okay, so what we're going to talk about today, failing any other questions, is chapter 12.5, and that covers the idea of how you talk about lines and planes from the standpoint of vector functions. So we're moving towards functions with vector outputs. So we're thinking we put in a parameter or some vector, and what comes out the other side is a vector. So one of the most basic objects in calculus is the line. After all, the whole point of calculus, I don't know if anybody ever told you this before, but the whole point of calculus is that everything is secretly aligned. That's the entire point of calculus. Tell me about that gateway to secret. The The point of calculus, the reason why you even care about lines, because the point of calculus is everything reasonable is secretly aligned. Oh, that's why you spent all that time doing tangent lines, right? A tangent line is a way of throwing away a function and replacing it with a line. Function sucks, put a line there instead. Lines are easy. So in order to do calculus with vector functions, we have to come up with some notion of what a line looks like in the vector setting. So in our regular old R2 graphs, we do something like this, and we say, oh, well, I'm going to take this dot and replace the function with this tangent line. It's easy to write down the form of this. This is just y minus y naught is equal to dy dx times x minus x naught. That's the equation of the tangent line, point x naught, right? I guess this has to be evaluated as x naught, but that's the idea. So I want to come up, the whole point of today is we're going to talk about lines because we're going to be using them when we start talking about derivatives of vector value functions. Okay, so yep, we're scratching. Okay, so what is a line? That's a good question. What is a line? So this is a line? That's a path between A and B. Shortest path between A and B. Yes, okay, that's correct. But is there a, I mean, I can't really do math with that, right? Like, oh, take a derivative, like, oh, find the shortest path that connects 2 points I don't know. So what is a line? What information do you need to know what a line is? What information do you need? A point on the line, right? So you need a point. Like in this form right here, what is this form called? Point slope, right? Okay, so what else do you need besides the point? No, not a slope. You need a direction is what you need. You need a direction. So you need a point which tells you where the line is. The reason I'm playing around with the word slope here is because slope isn't going to make sense as a number in a vector setting because we have things that can move in 3 dimensions instead of 2. So it's not enough just to know how tipped the line is. I need to know more than that. I need to know how it's oriented in space. Okay, so and we need a direction. In 2 variables, we call this the slope because it was just a number, right? I know something that contains information about direction. Vector tells me the way something points, right? So in vector land, the way that you think about what a line is, so I'm going to draw you a 2-dimensional picture here. We're going to make the vector formulation of a line be this. I have to have a starting point, and I'll call that point R naught. And you can think of R naught as being, this is a 2D picture, so I'm going to call it X naught, Y naught, but the same exact picture it's going to hold in 3 dimensions, right? And it's a vector. R naught is just some starting vector that gets me to a point in the plane. Now I have to be able to say, well, the line that goes through that point I'm interested in might look like this. So this is the line. If only there was a way I could figure out how to travel in that same direction from that point right there. The idea is instead of thinking about this as a slope where I have to count over X and up Y and over X and up Y and over X and up Y and so on. Instead, what I'm going to say is, okay, well, if this is R naught that tells me where to start, then I could point always in this direction. This is a vector. Every single point on this line has a vector that points the same way. If I started here and I said, how do I get there? Well, I go to travel down this vector. The vector points the direction to the next point, and it points to the next one. Maybe this is V. This is 2V. Double the length of V gets me another point, and triple the length of V gets me another point. So the way that you think about this construction is once you get to the line, always travel in the same direction as this vector V. But to get every single point, I have to stretch that vector V. I have to shrink it and stretch it so that it connects up everywhere else in the line. Does that make sense? Ish. So the picture I want you to have in mind here when I'm constructing the line is this. Go to your starting point with the first vector and then stretch a little bit. There's a point that's on the line right there. Or I could go to the starting point and I could stretch this much, and there's another point on the same line. Or I could go to the starting vector and I could stretch this much, which would be a different point on that line. Or I could go the opposite direction by multiplying by negative values. If I multiply by -1, I travel along the same vector, but in the opposite direction. Go to the point and then go this direction by multiplying by a negative number. And as you keep multiplying by negative numbers, you get points that are further and further out this direction. So the general equation for a line in the vector formulation looks like this. R of t is equal to R naught, that's your starting vector, plus t times v. So this you can think of as being your initial point. And this v right here, most people would call that a slope vector. It's not really a slope, but it's telling you what direction in three-dimensional space the line is going. This works in 2 and 3 and 4 and 5 and 15 dimensions, right? This idea. Everything that looks like this is a line. So this is the general formula. You take in a parameter, the function always starts at the same point, R naught. That's this vector, and then it stretches the vector v by multiplying it by extremely large values of t or extremely small ones or negative ones to sort of span out the rest of the line. All right, so as an example of what a line might look like. So here's a 2D example. R of t equal to 1, 1 times 2, 1. That's my initial point. And this is my direction vector. And if you were to plot this, when you're drawing a line, what you do is you always think, we should say, be careful here. We're always thinking relative to the origin. Vectors, we know we talked about a translation invariant, but we always think about moving from the origin to the line. So 1, 1 puts me right here. And then whatever I do, I'm going to travel in the direction 1, 2 from that point. So that means, okay, so I have to go up 2, over 2, 2, up 1. So all the V's, that's V right there. And the line, I make this back down. Well, I can see if I could do the chalk trick. This is R naught. This point right here is where you put the vector v, which is the direction vector. And then everything on the line is just stretches of this vector in this direction or in that direction. So this is a picture of this line. Of course, it has another name. You could actually identify what this vector is called in slope-intercept form if you want, because you know a point that's on here and you know how far you get from that point to the next point. So for this one, because we're in 2 dimensions, another way of writing this line would be y minus y naught is equal to m times x minus x naught. Y minus 1 is equal to, well, what's the slope? How far did I go from that point to get to the next one? I went up 1 unit and over 2. Up 1 and over 2. So this vector equation can also be thought about in this y equals mx plus b form, but there's actually a better way of thinking about this that will also work in 3 dimensions. So far we have r of t is equal to 1, 1 t times 2, 1. And also y minus 1 is equal to 1/2 times x minus 1. This is only true in 2 dimensions where we have the slope form. But I could think about this I could divide both sides by the numerator of this guy, right? It's a 1. But I should have picked a better function, I guess. But the idea is this is called the symmetric form. These are called the symmetric equations for the line. They contain the slope as part of the equations. This tells you how much the y, this tells you where the y started and how much you changed when you moved the increment of y by 1. This tells you where you started at x and how far you moved in the x direction for the same change in y. Make sense? And this is not a form you've ever seen before for lines, right? This one I'm sure you're well acquainted with. Most of you have probably seen this at some point. This is really useful in a lot of contexts because it cuts the equations down to single variable equations. So the set of points that satisfy these equations is the same line that I just drew right there. So in 3D, what this looks like, let's look at R3. If we're going to be looking at most of the next chapter is going to be in R3. These ideas do generalize to more dimensions. In R3, R of t is equal to x naught, y naught, z naught. That's R naught. Plus t times, what does the book use here? A, B, and C, I guess. A, B, and C. This is the vector B, the direction vector. So this is the equation of a line in 3 dimensions. You notice it's very similar to the equation of a line in 2 dimensions. I can't do this because I have 3 changes going on. X is changing and Y is changing and Z is changing. But what you can do is you can come up with equations that look like this that still contain the idea of slope inside. So let me show you how you do that. This is called the vector equation of a line. If you multiply through by t, you get what's called the parametric equation. So the parametric equation would say, well, if you think of r of t as being the variables x, y, and z, then you could write down that x must be equal to x naught plus at. Y is equal to y naught plus dp. Z is equal to z naught plus dp. And those are just 3 parametric equations, right? You give me a t value, I can tell you what your x, y, and z values are. This is called parametric equations. Vector equation, expand it out, and you get the parametric equation. If you solve these for t, so you can solve this for t, and you can solve this for t, and you can solve that for t, what you end up with is these equations. T is simultaneously, and if the same t must be true for all of these, right? I mean, if these things are, the idea here is you pick a t and it tells you the point. So one t is being plugged into all these. So that means simultaneously it must be the case that t is equal to x minus x naught over a, and also t is y minus y naught over b, and also t is z minus z naught over c. And now those look like these guys. Since the same t is in all of these equations, you can set them all equal to each other, and you get symmetric equations of a line in 3 dimensions. And all 3 of these ways of thinking about lines in 3 dimensions are used in practice. This one in particular is interesting because, again, over here, we sort of thought about slope as being the change in x underneath the change in y, right? dy over dx. So the same thing is being implied here, that the way that you're moving in your x, y, and z variables is for a change of a in the x direction, you do a change of b in the y direction, and simultaneously a change of c in the z direction. So it's not slope, but it's almost slope. So you can think about this as sort of almost slope form. Okay. All right, so what do you have to do with lines? Well, first thing you gotta do is find their equations. Any good mathematician, any good math student has found a zillion equations of lines in their day. So here is a new set of problems you can use to find equations of lines. So somebody might ask you, find the vector and symmetric equations of the line containing point 101, 3 minus 1, 2. This is the standard notation for a point. Is to label it and then tell you the coordinates. It's to distinguish it explicitly from vectors. How do I do that? I gotta start somewhere. What do I need? I remember though, what do I need to find the equation of a line? I need a point and direction. So I want you to imagine for a second, where am I going to find a point? Well, it looks like I have two of them, right? So I just pick one. The point is easy. We'll pick 101. Doesn't matter, I can pick either one. I'm going to get the same answer. Now I need a direction, which means I need a vector. Where am I going to find a vector that points between those 2 points? I could if I had the direction vector, but I don't have it yet. The idea here is I'm going to draw the world's worst graph of this problem. Here's the point 101. Notice how carefully I'm attempting to put this in 3 dimensions. There's the point 101. Here's the point 3 minus 1, 2. Totally accurate at the scale. How do I find a vector between them? I'll tell you how I'm going to find a vector between them. I'm just going to draw it. There's V, the vector that connects the 2 points. But how do I find it? I got 2 points. I want to know what the vector is between them. What do I do?
Find a different value.
Yep. So if I ever want to connect 2 points with a vector, I can just subtract their coordinates, right? 3 minus 1. It doesn't matter what order I do it in. No, because if I subtract in the other way, I'm going to get the arrow pointing the other direction. 3 minus 1, 0 minus negative 1, 1 minus, well, I screwed up the order there. 3 minus 1, minus 1, minus 0, and 2 minus 0. So 2 minus 1, 1. Oh. So that's it. I know that R T is equal to R naught plus QB, but I know R naught because I can use that point right there. That's 2 times this vector. One of the points was given to me. I can think of it as a vector to locate where the line starts. This is the direction that everything else in the line must be in because these are in the line. So every other vector must be collinear with those in the same direction from this one. To symmetrize this, you can either remember the form or you can solve it. The basic idea is it's actually pretty easy if you remember the point slope form, and you're going to be doing this. You can solve this for this form, which you think of as, again, I want you to keep this in mind. It's sort of a fake point slope form. Vector point slope form for line. And just write it down. X minus 1 over 2 is equal to y minus 0 over minus 1, which is equal to z minus 1 over 1. Symmetrized line. That's how you would solve this question. So at the very least, I mean, this is like we're doing 8th grade over again, but with vectors. All right, so let's do something a little bit harder. I'm going to pull on your teeth a little bit more to get you guys to talk. So a line, what was a line again? What 2 pieces of information give me a line? Point. Direction. Okay, so the other basic flat objects that exist in 3 dimensions, the other flat object is plane. Right? Planes are flat. Lines are flat. Planes are flat. So this is a plane. What information do I need to find a plane? A point, that's a good place to start. You definitely need to know where the plane is. So a point inside of it, that really helps, right? So to get a plane, you definitely could use a point P that lives inside that plane. What else? I'm just really deep. 2 more points. Points where vectors. Okay, so I got a couple of different suggestions so far. The first suggestion is if you had 2 more points, then you could make a triangle, and the triangle would tell you where the plane was, right? That's right, but it's not computationally as efficient as what we need to do, right? So we have a triangle. Really, so now somebody else said 2 vectors, right? 2 lines and 2 vectors. That'll get you something like this. But I mean, I don't want to write an equation down with 2 vectors inside of it.
No, like the borders of the plane.
The planes don't have borders.
Okay.
Planes go, I mean, so like when we draw them, they do, but you should think of a plane extends to infinity in every direction. So planes are infinite. So yes, if you were talking about some sort of finite subset, then knowing the boundaries would be enough, right? But think about this as a plane has, for us anyway, a plane has no boundary. In the same way that a line doesn't have ends, a plane extends forever in every direction. Okay, so 2 vectors inside the plane is almost enough information, but not very convenient to work with. Because there's a whole lot of vectors inside this plane to choose from. Is there a single vector that contains all the information inside the plane? Does anybody see what it is? So again, the issue I'm trying to point to here is, yes, if you knew 2 vectors inside of a plane, that is enough information, as long as the vectors aren't parallel to each other. That's enough information to figure out the rest of the plane. But it's hard to write an equation down that does that. Right? Ah, there you go. So here is the way that a mathematician or a physicist or an engineer thinks about a plane. Plane is a set of points that are all orthogonal to a single vector. There's one vector poking out of this thing, which I will call n. And the way that you think about a plane is, it's every vector that is perpendicular to that one vector. That's actually why two vectors are enough to get it. If you think about it for a second. That's what I'm going to ask you to do. But yeah, so the plane, one way of thinking about a plane is every vector perpendicular to a, the word here is normal. Starting at a point P. So you start at the point P, and then you say, okay, I'm going to test this vector V. Is V if V is in the plane, but this is normal to the plane, then we say, okay, well, those are perpendicular V's in the plane. These are perpendicular W's in the plane. These are perpendicular. Every vector in here has to stay at a right angle because all you're doing is rotating. Rotation doesn't change angle, right? So this vector n, not coincidentally, is called a normal vector. And so all we need to do now is to take this idea that every vector v in the plane is perpendicular to the normal vector n. So we're going to take that idea and we're going to turn it into math. Very nice equation, the nicest possible equation for a plane. If you guys have learned, I'm going to put it over here, it's such a bad equation. Most people that have studied planes before have seen this. That's terrible. Don't carry that around your head. X plus by plus cz is equal to d. This is, I mean, this is sort of an early idea of what a plane is. It's equivalent to what we're going to be doing, but it doesn't really contain a lot of information. It's hard to compute with. I mean, I don't know. Find x's and y's and z's that solve that equation, and I guess you find a plane. So what we're going to do is we're going to use the fact that now we know what the dot product is. So to say that every vector in the plane is perpendicular to the normal vector is to say that if p is in the plane, then n dot v is 0. The dot product can be used here. The most elegant way of characterizing planes comes from the use of the vector dot product. We have one more step to go, which is I need to characterize v. Now notice v here does not include information about this starting point. So what I'm going to do is I'm going to write v as being equal to the starting point, which is r naught, plus a direction vector r. This is going to be sort of the unknown object here. Starting point. You add another vector to your starting point, then it's like, I'm going to draw a picture of this in a second. This is sort of the direction. So the picture we have now is this. You've got some vector that points up to the plane to the point r, the vector r naught. It sits inside the plane. Then from there, you add some other vector to it. R naught plus r. If the thing that you get when you do that is perpendicular to this vector n, then this was in the plane. If it was not equal to 0, it's not in the plane. So the idea is we want to characterize, we need to use this fact that we know a point in the plane. We're testing all of these vectors that come out of R naught to see if they're perpendicular to the vector n. So we write n dot r minus r naught equal to 0. So like, yeah, I guess the idea is r minus r naught is the connection between these two. Doesn't matter, plus minus is the same. Because if this is R, then this is R right here. This vector is R minus R naught. So R naught gets you to the point you know is in the plane. R gets you to some other point that may or may not be in the plane. And what you're testing is the vector that connects the ends of those in the plane or not. That make sense? Lost anybody in the geometry here? I'm trying to go too fast. So this, no, so what are the unknowns in this equation? You know this. This is known. This is like the slope of the plane. It literally tells you what direction the plane is pointing in. This is known because that's the initial point. So if you're willing to use the dot product, this is basically as simple an equation as the equation for a line. It's a way of characterizing a set of points in 3 dimensions in terms of a starting point and a vector. So an example looks something like this. An example. Find the equation plane with let's say containing point 1, 1, 2 and perpendicular to the vector 1, minus 1, minus 3. This is about the easiest possible example you can be given here. That means this guy, your initial point, tells you what the R naught must be. And perpendicular to the vector means as soon as you see perpendicular to a vector, that's the normal vector. And then what we're testing is these other vectors are, this is the unknown. So R, which is the unknown, I think of as being all of the X, Y, and Z values that may or may not make this true. So remember, the R's are the vectors we're testing to see if they sit inside the plane. And so the equation of this plane looks like this. 1, minus 1, minus 3, dotted with X, Y, Z, minus 1, 1. N dot, is equal to 0. That's be an equation. N dot R minus R naught 0. It's a little bit hard to work with, but in terms of like thinking about the geometry of what's happening, this is the clearest formula you can write. Planes are characterized by their orthogonality to a normal vector. Okay. So what if I don't give you the normal vector? Somebody earlier said all you need to know to find out like what the equation of a plane is 3 points. So let's put ourselves in that scenario. What happens if I only have 3 points in a plane? How can I discover the information that I need? Now, suppose I just tell you, oh, I got a plane and it contains, I don't know, 1, 1, 1, 0, minus 1, and 3, 1, 0. I don't have a lot to work with here. No vectors, no normal. I mean, I know I got a point inside the plane. Okay, so I'm going to draw the world's worst picture again. Got some plane. I'm going to put this point right here. I'm going to call that the point 1, 1, 1. And over here, I have the point 2, 0, minus 1. Notice it doesn't actually matter if this is accurate or not because the geometry works regardless of if this is plotted consistently on a 3-dimensional axis. There's 3 points. To plot a plane, I need to know a point in the plane. That's easy. And then a normal vector. Where am I going to get a normal vector? If only there was a way to produce a vector perpendicular to other vectors. The idea is if I knew this vector and I knew this one, that's two vectors that are inside the plane. And if I could use those vectors to produce one that was perpendicular to those, it would have to be perpendicular to everything else in the plane as well. So where is n going to come from? What can I do to V and W to produce an orthogonal vector? Cross product. So the game we're going to play is if I had a vector V and I have a vector W, I can find a perpendicular vector by looking at V cross W. And that I can use as a normal vector. So you can build the vector version of a plane from the points that are contained in it by figuring out what the vectors are and then taking their cross product to get the normal vector. Okay, so if we started with 3 points, we got points, but I need a normal vector. Step 1 would be to figure out V and W. So V, I'm going to subtract this vector or this point from that one to get this vector, this one right here. 2 minus 1 is 1, 0 minus 1 is minus 1, minus 1 minus 1 is minus 2. That is this vector right here. So V is 1 minus 1 minus 2. That's V. W, so I got this by taking, say this is P, Q, R. This is Q minus P. The vector between 2 points is their difference. I get W by subtracting any 2 of the other points I want. I'm going to take R minus Q, doesn't really matter. Or I guess in the picture I drew here, it's actually R minus P. This is the point R, and this is the point P. In the picture I drew, I'm going to do R minus Q. This gets me 3 minus 1, which is 2, 1 minus 1, which is 0, 0 minus 1, which is minus 1. Now I have to go through the arduous process of crossing those vectors to get them. Step 2. Find n. Means V cross W. Now normal vectors aren't unique at all because all I need is the direction, not the magnitude, right? So it's possible you can approach this problem for a lot of different ways and you're going to get different vectors, but they're all going to point in the same direction, even if the magnitudes are different. All right, so let's cross them. E cross W is the determinant of I, J, K, what's the V I got there? 1 minus 1, 2, and W is minus 2. And W is 2, 0, minus 1. So I should just write this down instead of trying to compute it. 1 minus 0, so it's 1I, negative 1, plus 4 is 3, minus 3J, 0 minus negative 2 is 2, plus 2K. That's n. We started with 3 points. We used the 3 points to produce 2 vectors. We use the 2 vectors to produce an orthogonal vector, and that's enough information to characterize the plane. So the equation of the plane can be written 1 minus 3, 2, dotted with x, y, z, minus any one of the starting points. Let's just do 1, 1, 1. That would characterize the plane. Normal vector that we got from the cross product any one of the starting points to make sure we're located correctly in space. And then it's the set of all points that satisfy this. So what I'm emphasizing with this approach here is not computability, but geometry, right? The idea that a plane is a set of things that are orthogonal to a normal vector. From a computational standpoint, though, actually, so before I blast on here, is this okay? Yep. It doesn't, I mean, I'm thinking of points and planes as being interchangeable, or points and vectors as being interchangeable. They are if you consider the origin as the fixed point that you're working from. Yeah, so later on in other classes, like the book goes out of its way to emphasize these angle brackets for vectors, but they're not strictly necessary. Okay, so this stuff is great. The geometry is awesome. The fact you're working with a normal vector is cool. But we want to do something more computational here, which is if I took this equation and I solved it by actually computing these dot products and expanding them out. So if you expand this, if you expand n dotted with r minus r naught 0, you get what are called the scalar equation of a plane. This is the vector equation of a plane because it's vectors and dot products. A more typical thing that you may have seen before is called the scalar equation. Let's look like this. A times x minus x naught times y minus y naught times z minus z naught 0. Where does that come from? It comes from doing the subtraction and then actually just computing the dot product. Want to see where this comes from? Think. ABC dotted with x minus x naught, y minus y naught, minus z naught. That's n. This is r minus r naught. So the normal vector told me the direction. The r is my variables x, y, and z. The r naught was my initial point, x naught, y naught, and z naught. If you actually compute that dot product, you get this. This is what most people learn when they see it the first time. So this equation, the scalar equation of a plane. And to get all the way down to what you guys have seen before, that one, that terrible equation over there, the linear equation of a plane, you just multiply this out and throw everything that doesn't have x, y, and z on the other side. So if you multiply this out, ax minus ax naught plus by, I'll just do it. Ax minus ax naught plus by minus by naught plus cz minus cz naught is equal to 0. That's a constant, that's a constant, and that's a constant. So where does the d come from in that equation? It's just all this crap added together. Ax plus by plus cz is equal to d, where d is equal to ax naught plus by naught plus cz naught. Why do I hate this version of the plane? Because it throws all this information away. We lose out where we start the plane when we do that. This is like doing the y equals mx plus b version of a plane, where I don't know anything about what's in the plane. This is like the point slope version of the equation of the plane. I've got the slope in the sense that I've got some vector that tells me the direction, and the x naught, y naught, z naught, which tells me where I am in space. So this is called the linear equation. These are sort of the fundamental objects that we use when we're studying derivatives. So I should motivate why we're studying flat objects. Derivatives are a way of replacing things with flat objects. So when I do derivatives and I'm working at higher dimensions, I need to have curves and surfaces, curved objects in space, but I want to replace them with flat stuff. So curved lines, curves, like coily dudes like this, locally I can say, well, I can replace a curve with a tangent line. And if I have a surface, like a sphere, well, what's the flat approximation to a round object in space? Well, the flat approximation isn't a line anymore. The flat approximation is a little plane that's right next to the curved surface. So these are the central objects that come out of derivatives when you're talking about objects in three-dimensional space. And that's why we need both. Okay. All right, so next time what we'll talk about is there's a couple of applications of planes that are really, really useful that we haven't gotten to yet. But these are the basic objects. The geometry is just as important as the sort of relatively trivial computations here. So I want you to try as much as possible when you're wrestling with these questions to think about what it is that you're doing with these normal vectors and these direction vectors. Okay. And then once we have this all machined up, then we'll start actually doing approximation of derivatives in three dimensions. All right. Yes. Get some sleep.
I just had a question. I came in kind of late and I was curious about I saw you had stuff about the final and then the next test. I was just wondering if you could just reiterate that.
Yeah, so I mentioned that the final is in, I just said that like we've got 3 weeks of left, basically 2 weeks of course left. There's a exam on Friday next week, but mostly the announcement there was just to remind people it was coming up and that I would be talking about it in detail on Monday.
Oh, okay, perfect. Thank you.
Yeah, we're doing a quiz now, yeah.
Okay, thank you.
Yep.
Yep.